Hello everyone, Dr. Hasbullah here, and in this video we are going to be looking at how to use the knowledge of potential function and stream function in order to analyze a few types of flow. Specifically, there are 4 types of flow, which is called the uniform flow, source and sink, a rotational vortex, and doublet. Now, these 4 types of flow has been specifically chosen so that you can see exactly how potential function and stream function can be used to solve the flow field. But before that, let's take a look at the definition of Cauchy-Riemann equation again. So U is equal to del psi over del y and also equal to del phi over del x, isn't it? And if you look carefully, the relationship between potential function and stream function is actually perpendicular to each other. So if I have a flow that looks something like this. This is a pipe, okay, and a flow coming from the left. So if I have a stream function, one stream function and two stream function that looks something like that. So this is my stream function number 1 and this is my stream function number 2. My velocity potential will look something like this. It will be perpendicular to the stream function. Okay, so this will be phi 1, phi 2, phi 3, and so on and so forth. I thought this is interesting to tell because later we are going to try to plot both stream function and velocity potential in those 4 types of flow. The first type of flow that I want to show you is a very simple one, which is called uniform flow. And for uniform flow, the stream function is very simple. This is psi equal to u infinity y. So u infinity means the free stream velocity. And for the velocity potential, it is equal to u infinity x. Now, let's try and plot this uniform flow. If you have a plot that is in x and y direction, and a uniform flow means that the flow is going parallel to x direction. Okay, and this is what your stream function looks like. So your stream function is here and this is equal to constant. So this is stream function number 1, stream function number 2, number 3, and number 4. So because we know that our velocity potential is just perpendicular to the stream function, so our velocity potential plot will look something like this. Okay, and this is psi 1, psi 2, psi 3, and psi 4. Now, this is the definition of this flow using a stream function and also using the potential function. So, what if I want to find the velocity in x direction or u? Okay, so u is equal to del psi over del y, isn't it? Which means that when my psi is u infinity times y, my u will be u infinity or the free stream velocity. Okay, so this is my u infinity. And my v, that is the velocity in y direction, and this is equal to del psi over del x, and this must be equal to 0. And as you notice in this plot, there is no velocity in y direction. There's only velocity in x direction, which is why it explains that our u has values, but our v is 0. And we obtain this using Cauchy-Riemann relationship. Now, what if I want to plot this uniform flow in polar coordinate? What does the stream function and potential function looks like? So, psi in polar coordinate is equal to u infinity, and of course, y is simply equal to r sine theta. So, this is r sine theta. And my phi in polar coordinate is u infinity r cos theta. So, if I were to obtain my velocity in radial direction, so this is equal to, let's take a look at my Cauchy-Riemann equation. So, this is it. So, 1 over r del psi over del theta. So, this is 1 over r del psi over del theta. And this is equal to differentiation of this one divided by r. So, this will be u infinity cos theta. And to find my v theta or tangential velocity, I need to use this equation. Okay, so this is negative del psi over del r. So this is simply B negative del psi over del R. So that will be U infinity sine theta. Okay, so that's it for uniform flow. There's nothing much to it. You can easily find the velocity in x direction, velocity in y direction, velocity in the radial direction, and velocity in tangential direction. Now let's take a look at another type of flow, which is called sink and source. Now the string function for sink, let's write this here. So sink and source. And for source, the string function for source is equal to psi equal to q over 2 pi theta, and the potential function phi is equal to q over 2 pi ln r. Now obviously this is in polar coordinate. So let's take a look at what a source would look like. So a source must originate from a single point. Okay, and from here it goes to all the direction. Okay, and that is my source. Okay, so this is called source. And of course, if we consider theta here equal to 0 and it goes positive in counterclockwise direction, so here I will have, because this is psi equal to q over 2 pi times theta, so my psi here is 0. And if this is what my string function looks like, what happens to my potential function? So as we know, potential function is just perpendicular to the string function. So if I were to draw my potential function, it should look something like this. Right? And this is my potential function. And for sink, simply the equation will be negative. Okay? So for sink, then psi equal to negative q over 2 pi theta and phi equal to negative q over 2 pi ln r. So instead of the flow going outward of that center, it goes inward towards that center. Now let's see what happens to my velocity components. So in polar coordinate, you have two velocity components, which is the radial velocity and also the tangential velocity. So my radial velocity here, Vr, is equal to, let's take a look again at our Cauchy-Riemann equation. So Vr is 1 over r del psi over del theta. So 1 over r del psi over del theta. And this is equal to 1 over r. What is del psi over del theta? Del psi over del theta is equal to q over 2 pi. So this will be equal to q over 2 pi r, and that is my Vr or radial velocity. Next, let's take a look at my tangential velocity. I suspect tangential velocity will be 0 because in source flow, the flow is going outward. There is no tangential component. But let's take a look and let's see what is our Cauchy-Riemann equation for tangential velocity. So I believe this is negative del psi over del r, and therefore this is minus, so del psi over del r of course is equal to 0. So our tangential velocity is definitely 0. And now that we have the tangential component and radial component of velocity, what happens to the velocity in x direction and velocity in y direction? In situations such as the source and sink, it is almost not making any sense if we are to represent this in Cartesian coordinate because the flow is moving outward. So to represent this in polar coordinate makes a lot of sense. But if you really need it to be in Cartesian coordinate, our velocity in x direction will be u equal to q over 2 pi times x over x square plus y square. And our v will be q over 2 pi y over x square plus y square. And I do believe this is a little bit too complicated to represent source and sink in Cartesian coordinate. Okay, now that we have looked at uniform flow and also the source and sink, let's take a look at the next type of flow, which is called the irrotational vortex. So, irrotational vortex is represented by a string function equal to capital gamma over 2 pi times ln r, and the psi is capital gamma over 2 pi theta. And I think you can almost see the similarity of this equation with the source and sink equation. It seems like the relationship has been reversed. For example, you see ln r here, but now you see ln r in string function. Okay, and gamma here, this is called capital gamma, and this is what we call a vortex strength. So this is vortex strength. And I forgot to mention you before, Q is also called the source strength. Okay, let's go back to irrotational vortex, and gamma is represented as the integration over the closed curve of velocity dot ds. Let's not worry about this first, and let's take a look physically what irrotational vortex looks like. So irrotational vortex looks something like this. So you have a multiple circles that goes around each other. And let's say that this goes counterclockwise. And if you have a center here, and if I want to draw x and y coordinate, so this is x and this is y coordinate, what you have here in terms of the velocity component, this is a reversal of the source flow, isn't it? For source flow, you have the radial component of velocity, but you do not have tangential component. But for irrotational vortex, you basically have the tangential component, but you do not have the radial component. Let's try and prove it using Cauchy-Riemann equation. So VR is equal to 1 over R. I think we should remember this by now. Del psi over del theta. And this is equal to 1 over R. What is our psi? Psi is gamma over 2 pi ln r. Let's not mistake this gamma with r. So gamma is the vortex strength and r is the radius. And for this equation, this becomes 0. So as expected, our radial velocity is 0. And what about our tangential velocity, v theta? V theta is related with the string function as negative del psi over del r. So now my v theta is, differentiate that with respect to r, so this will be minus capital gamma over 2 pi r. So this means that if I were to label this, my v theta is equal to minus gamma over 2 pi r, which also means that the larger the radius, the slower my tangential velocity will be. If the radius is very close to the center, then my tangential velocity will become very high. And again, it is very simple to represent this in terms of polar coordinate, but if you really need to represent this as Cartesian coordinate, your velocity in x direction will become u equal to minus gamma over 2 pi y over x square plus y square, and your velocity in y direction v is equal to gamma over 2 pi x over x square plus y square. And I believe this is simply the reverse of what you have for source and sink, isn't it? Right, so moving on to the last type of flow that we are going to be looking at, and that flow is called a doublet. And for a doublet, the string function is psi equal to minus mu sine theta over r, and the velocity potential is phi equal to minus mu cos theta over r. Now, based on what we know, we can actually already try to find what is the radial velocity and also what is the tangential velocity even without knowing what a doublet physically means or what a doublet physically looks like. Because whenever we have a stream function or whenever we have a velocity potential, we can always find the radial velocity and tangential velocity and also u and also v just by using the Cauchy-Riemann relationship. So let's do just that, and I will show you what a doublet looks like later. But before that, the mu here is definitely not viscosity, but it is called the doublet strength. So now our VR, let's write it further down. So VR is equal to 1 over R del psi over del theta. So this becomes 1 over R del over del theta minus mu sine theta over R, and this is equal to 1 over R square times mu cos theta. And if I write this properly, I will have, I think we are missing minus here, so this is minus mu cos theta over R square. And my V theta is equal to del psi over del R minus, so V theta equal to minus del psi over del R, and this is equal to minus del over del R of this one. Okay, so this is minus mu sine theta over R, which will become equal to minus mu sine theta over R square. And if you want to represent this as a Cartesian coordinate, I'm just going to write it here. The velocity in x direction, or u, will equal to minus mu x square minus y square over x square plus y square, and everything is squared. Okay, and the velocity in y direction, or v, equal to minus mu times 2xy over x square plus y square squared. Now, this is definitely more complicated than the Cartesian coordinate of velocity for source and irrotational vortex. Now, let's take a look what a doublet looks like physically. A doublet by itself, if you must know, does not really look like anything. It is quite hard to explain what the doublet looks like. But if you are to imagine that you have a sink and source. Okay, so a sink and source that is very close together. Okay, so what happens is that this source will go to the sink. It goes something like this. Okay. Right. And let's say that this source and sink is now very close together. What happens is that you have one center and you have a flow that looks something like this. Okay, and that is your streamline. Right, so this is your psi 1, psi 2, and psi 3. And of course, if you are to plot the potential function, it is just perpendicular to that psi. Okay, so your potential function will look something like this. Okay, so by its own, you can say that a doublet doesn't make a lot of sense. But later, we are going to see the combination of these flows. For example, if you combine doublet and uniform flow, then you will see something meaningful over there. Okay, but before we go to that level, let's take a look at an example involving irrotational flow and how we can use the radial and tangential velocity that we have just learned to solve this problem. Let's take a look at that. Okay, so example. Okay, let's say that you have a tornado. And a tornado can be almost accurately represented by a rotational vortex. And let's say this goes in clockwise direction. And it is given that the pressure away from that tornado, let's say here. So P here is equal to 0 gauge. And it is also given that the velocity at 20 meter from the center of tornado is equal to 20 meter per second. And now the question is asking you to find what is the velocity and pressure at 2 meter, which means the velocity and pressure 2 meter from the center of tornado. And my initial guess, because we have seen the velocity for a rotational vortex before, we know that as the radius got smaller, the velocity will become higher. And I think this makes sense for a tornado. The closer you are to the tornado, the faster the velocity that you will feel. So let's take a look at our rotational vortex just now. And we know that for rotational vortex, the VR or radial velocity is 0 and V theta is minus gamma over 2 pi r. So let's use that. V theta is minus gamma over 2 pi r. So we know that the velocity here is actually V theta because VR is simply 0. Now, what do we do about this information? Now, from this equation, what I can do is to find the gamma. This is equal to 2 pi r times V theta. So this is 2 pi times r is 20. And at 20 meter from the center, our V theta is 20 meter per second. We are simply using this information. So this is equal to 20 times 20 is 400 times 2 is 800 pi, and this is minus, and the unit is meter square per second because you are multiplying distance with velocity. Now that we know that the gamma is minus 800 pi, this will be constant anywhere inside the tornado. So at 2 meter, my velocity is equal to minus capital gamma over 2 pi r. So this will be minus 800 pi over 2 pi r. R is 2 meter. Now, I can cancel the pi out. I can cancel the negative sign. So now 800 divided by 4 is simply 200 meter per second. And that is a very high velocity. 200 meter per second is about 600 kilometer an hour. So that's very fast. You don't want to be anywhere near that. Okay? The second question is looking for pressure. And whenever you need the relationship between velocity and pressure, you know that the best equation is Bernoulli equation. So using Bernoulli equation, that is P infinity far away from the tornado plus half rho u infinity square equal to P 2 meter from the tornado plus half rho u 2 meter from the tornado. So P away from the tornado is 0 gauge. Okay, so this is 0. And the velocity away, far away from the tornado, we can also assume it to be 0. So this is 0. So that leaves us P equal to minus half rho u square. And u is definitely V theta that we obtained before. And this is at 2 meter. So at 2 meter. Right? So this is equal to minus 1 over 2. And rho of air, you can just use 1.2 or 1.23. U is 200 meter per second. And this is equal to 200 square divided by 2 times 1.2. Negative 24,000 Pascal or minus 24 kilopascal. So does that make sense that the pressure is negative? A negative pressure means that the condition 2 meter from the tornado is vacuum. And this vacuum sucks everything inside the tornado. That's why roofs are falling apart and everything is going into the tornado. It's because of this negative pressure. So definitely negative pressure makes sense for this problem. I hope now you can see how can we use the 4 types of flow, which is uniform flow, source and sink, rotational flow, and doublet to solve simple engineering problems. As long as you know the stream function or potential function of these types of flow, you can use it in order to find the radial velocity, tangential velocity, u and v to solve any problems. And whenever you have that velocity, you can use that to find your pressure using Bernoulli equation. In the next video, we are going to be looking at the combination of these 4 basic flow. For example, you can combine uniform flow and you can combine it with doublet. Or you can combine uniform flow with doublet with rotational vortex. Then it gets really interesting. And for that, you need to get yourself really familiar with these 4 types of basic flow and understand how you can derive the velocity components from the stream function of this flow. That is all from me for now, and I'll talk to you soon. Bye!